Hello, everyone. So after we saw that presentation, I'm going to try to slow down a little bit. That was quite technical. So for this one, it's going to be a little bit more simple. So we're going to be talking about governance designs for L1s, and especially what Owen just mentioned, the validator signature contract that we will be using to manage some changes in different protocols. So first of all, what is governance and why does it matter? So why are we here in the first place? So after asking different sources such as Wikipedia, Google, and even ChatGPT, they all come together to say that the governance is the system that we use to make collective decisions. So what this means in terms of blockchain is how protocols evolve and who has a say with that change that the protocol is changing. So there are like different ways why we want to change a protocol once it's set in the chain. And the first of all is the protocol can evolve. So the market is dynamic, the world is dynamic, and why the protocol is not dynamic. So sometimes a protocol needs to evolve in order to fit a specific market needs or a specific security needs as well. So if there's any concern about any security and an upgrade that you need to do, you better have a plan to do that and not make everything so static that it cannot change or face different type of risk after you deploy that. And the last part is important as well is the sense of belonging. When you have a governance system, and when we talk about decentralization, this is not just like a technical approach to things, it's also a cultural approach. So sometimes a protocol would be wanting to do this kind of governance systems to bring the community on board as well and take part on the decisions on what is going to happen with the protocol they are owning in some way. So it's basically giving a voice to every stakeholder that it's involved in some way in the protocol itself. Well, this kind of feature is not, we will see in a bit, is not quite met in the validator governance system. It is actually good so you know who you are giving a vote or a voice into this kind of changes. So first of all, let's gonna go through some common governance models. So we have the token-based governance, where not always one token equals one vote, but we have different models where we can have like quadratic voting, some sort of like if you give me, I don't know, like your identity, you will have a little bit more of a vote if you were not to give me that identity or so on. So there's a lot of different modifications on that, about that token-based governance. The good part of it, or a pro that it has, is that it has some sort of incentive alignment towards, like if you're holding the token, you're usually willing to make good decisions on the protocol because that way you'll be affected if that decision is not good. So you have like a proper incentive alignment. The bad part is that it has proven like low participation ratios. So that is one thing. And the other thing is like sometimes people get the tokens just to speculate on them and not actually participate actively in those protocols. So that is one challenge that those token-based governance models have. We also have the delegated DAO councils, which is basically you delegate your vote to someone you trust, and they will take the decisions for you. And the thing here is, it makes it a little bit easier for those that are participating in the governance to participate because it's a little bit easier. There are usually those that you delegate that power are a little bit more active than just like random holders that have that token. So it reduces the voter fatigue, and also the bad part of that is that it can introduce some political issues, or you can sometimes like have some opinion regarding your own specific incentive, let's say. The other thing is these multi-sig committees where you usually have a few members that take the decision. You are like a trusted member of this committee, and you need to sign a transaction in order for that change to happen. This is fast and efficient, but unfortunately, if you have like it usually is a centralized system, it's not scaling good, to be honest. So it's centralized and sometimes opaque. Last but not least is what we will be covering right now is the validator-governed systems, which is basically handling that control to your validator set. So the cons about this is that, remember the point that I say here about sense of belonging? Well, in this mechanism, you are not giving a voice to everyone, but just to the validator set, which can be what you want. So what I'm saying is that all these systems have some sort of trade-offs, and you need to decide depending on what are you going to implement and what type of changes you want to see in the future and how this is going to come all together. The pros about this, and I think I skipped that part, is also we have aligned incentives. Users are also technical. They know how to run a node, so they can probably know how to manage all this infrastructure properly. So there won't be a lot of issues that you will have if you were to set or leave this to any common user, let's say. So what I'm presenting, as Owen mentioned briefly, is you know how multi-sig work, and this government system is pretty similar of a multi-sig committee, but the committee is not just a few signers, but instead the validator set. So how a multi-sig works, and for those that are a little bit new to this, you have some users, or you have some wallets that are owners of a multi-sig contract, and this multi-sig contract act as a wallet to send some functions or send some transactions to trigger specific functions on a dApp. So this dApp is the one that we are targeting, or we are doing some voting on top of that. The thing is that if you want to add or remove any of these signers, you need to create a transaction as well. And this set of signers are not dynamically changed in any way. And the same multi-sig contract regulates itself from adding or removing these signers as well. So an option to have these kind of wallets within your L1, which is also great, is this via the Ash wallet powered by, this was like a fork from the Gnosis Safe wallet, that you can enable that in your own chain. This is like a smart contract wallet, just EVM, as I don't know if you have played with this Gnosis Safe, but it's just basically that. But the Ash guys enable that for L1s. And when we talk about this, instead of having a list of signers, but instead that having that power to be sent to the validator set, then we have this validator set signature, which is going to act as our multi-sig wallet in some way. But again, like instead of having multiple signers as a list of signers, you'll have all the set of validators. And then you can control or interact with those dApps smart contract in order to meet the specific security needs that you want. So having a little bit of a comparative table here. So in a multi-sig, you have M out of N signers that will be required to process a transaction, while in the ICM governance or validator governance, you will have a percentage of the network stake that is required to sign a transaction in order to create a change or interact with some specific functions. Then the custody about this is if you are saying a multi-sig, you have like a manual custody of that. You can have like, I mean, there are different ways that you can custody that wallet, but it's just basically like a manual custody of a wallet. While in this, you can have some automatization of chain, which is actually what we do. We're going to see it in a bit. The messages are signed off-chain for this governance and how is this implemented. The other thing is decentralization. Again, as I said, it's just a few set of signers, while in the validator is just like dynamically adjust as the validators come online or not. Security as well, you can have like individual ECDSA, or and for the governance one, we have the validator governance. We're using BLS signatures. Also, we have the scope of multi-sig are usually for contracts that are deployed on the same chain that the multi-sig contract is deployed, while in this validator governance, you can interact with other chains. So you can basically have your own chain taking decisions. There we go. I'm going to move here. So you can basically have a chain A with a set of validators and a contract that is deployed on chain A as the main, let's say, signature contract, and then the smart contract of the dApp that you want to have some power on, deploy on another chain. So how do we enable this validator off-chain signing? And this is especially useful in terms of whenever we see a transaction happening with ICM or any cross-chain messaging, it's usually because something happened on-chain that will make you sure that we all agree that that transaction happened as a validator, so then we can trigger some action. But in this case, we are having that changes or that transaction going to be signed off-chain. So the simple answer is we enable ICM or warp precompile to verify those signatures. So for those that are not too familiar with Avalanche, that basically this we have the P chain, which acts as a common signature directory where we can get which validator is signing with which key, and we are having also a sense of the stake that they have. So how this works is we have the P chain with all the list of validators that are validating each of these chains, and we have the weight of those. So an aggregator, and I'm going to cover in a bit like why we need to aggregate those signatures, gets and collects all the signatures of all the validators to sign the off-chain message that is coming over here. And then we have like a message that is already signed, and we all agree that that message got signed. So a little bit and super quick about signatures, and just to explain why we need to aggregate them, is the signature scheme gives us authenticity, non-repudiation, and integrity of the data that we are working in. And it has basically, it can act as a wrapper around any type of data that we have that gives us all those properties for security on that the message hasn't been tampered with, that the message is coming from who says it's coming, and there's no one else that could have sent that message without the private key. So like a regular signature scheme has these three properties. You can generate keys. You will get the secret key and the public key, and you will be able to sign and verify those messages. If you have a message and a secret key, you will be able to sign that message. And if you have the signature, the message, and the public key, you will be able to verify it, that it comes from who says that it was signed. But what happens if we need to collect a bunch of signatures in a single message? Well, it can get a little bit like if it's only 7 signatures, it gets, we just add them to a message, but that can get a little bit complicated when we grow in number of signatures that we require. So imagine just like one single message that has is 64 bytes, and the signature is 48 bytes. Well, if we need to collect 1,000 signatures, then for one single message, it gets like super heavy. For just like a single 64 bytes, it gets like 48,000 bytes. So that is why we don't want to have or be working with a ton of signatures, but instead have the aggregated ones. So we have the signature aggregation that essentially works like as if it was just one single signature. So we can have this aggregate signature with multiple individual signatures that will get us the aggregate signature, as well with a public key that can be aggregated into an aggregated public key. And then we, of course, have the verify function that we can return if we pass this signature, message, and the aggregated public key. It will return if that corresponds to what it says. So getting back to how these flows works in terms of our validator signature. So we have this message that has been aggregated with the signature. And whenever you want to trigger a dApp, the design is basically giving ownership of this contract to that contract that is the validator set sig. So if this validator set sig is the only one that has control over that contract, this will require a message that is signed by all the validators and the threshold that it requires in order to actually send this transaction to the warp precompile. The warp precompile is going to read from the signatures that are on the P chain and will verify if the message is actually being signed properly. If that is the case, then the warp precompile will return, like, yeah, this is a valid message. It was signed by the threshold that we set in the configuration of our nodes, and it will be able to trigger that action. So how does this look like? So this is the structure of the message. And first of all, we need to decide the payload to forward to the smart contract. And here is an example of the call data that we have, for instance, for minting some ERC20, that the ERC20 token has been restricted, or the mint function has been restricted to the validator set sig contract. So basically, you're telling, like, if this, I mean, this is the message that has been gated by this only owner, and only this validator set sig contract will be able to trigger. So you have this a specific instruction, and then you need to wrap that around the validator set signature, which will add on top basically which blockchain you are targeting and what contract you want to trigger that. So basically, this target contract address will be the ERC20 contract deployed. The target blockchain, again, because you can have governance on other chain that is not the one that you have deployed, you need to specify which chain you are sending this to. And also, who's going to be in charge of telling, like, yes, the signatures are correct and everything is working properly. And we also have a nonce property here, which is basically for security reasons, so you don't have a message being executed twice with the same nonce. Finally, the value that if you need to send some value to the function, and the payload if you require it as well. So that payload is basically these instructions. And on top of that, you wrap it again, so it has the form of a warp message. So this warp message can be signed. It will need the source chain ID, the origin, sender address, and the payload. I mean, this, you don't need to pass this one, but the payload is basically all the rest that you have. So with all this structure, so you define the payload on the instructions that you want. You generate the message, including all the manager contract, target blockchain ID, target contract. And then you need to say, like, OK, this is not coming from an on-chain activity. So how are we, like, agreeing on that state? Well, we need to include the message in our config file from each of our validators. And if that validator gets that configuration of the message, so you basically need to put all this in the config file, here in the point tree, of the validators. Then if a contract, if you try to execute that call, you need to provide that, and the validator will be able to sign that transaction that is coming or is already in the allowed list of transactions in your configuration. Once you have set this, you should be able to do the complete flow, and it will agree that it will interact with the precompile. But this is just the developer experience. If you want to do this, you will need to define all these steps, but you don't need to mess with the warp precompile, the signature aggregation, or so on. You just basically need to define what you want to send and just add that to your validator as well. So some use cases of this is basically upgrading any critical components, such as important bridges that you can have, especially if you have like native interoperabilities, which is the case for Avalanche. Also critical oracles, or any critical component that you want to give control to the validator set. Also to manage some precompiled contracts, such as allow list, native minters, gas manager, and so on. Something else could be granting DAO funds access as well. And of course, like network component upgrades, such as the validator managers, can be owned by the validators as well, instead of a multisig, or any components beyond L1, such as like super simple case. It's just like for L2s, you see how you need a multisig in some way. Well, you can manage that in a validator set instead. So that is the whole flow, and I'm running out of time, but I think we're finished. So if you want to know more, we're building a lot of courses around interoperability. We'll have also a talk tomorrow about that. So make sure to join the Build a Hub and don't miss any of the courses. Thank you so much.